Hello, discrete math fans. Let's do an example problem. We'll define a relation R on the natural numbers by saying that for all A and B in the natural numbers, A divides B. Is this relation reflexive? And we want to prove or disprove this. All right, well, let's start with a natural number n. We know that n divides n, so that means n is related to n. That's it. That proves that R is reflexive. That's the whole proof. Well, let's do another one. Let's define a relation G on the integers by saying that for all A and B in the integers, B is bigger than A. And is this relation reflexive? We'll prove or disprove. All right, now this relation is not reflexive. And in order to prove this, we'll just show a counterexample. We know that 1,729 is not greater than 1,729. So that means the ordered pair 1729, 1729 is not an element of G, and so G is not reflexive. Now you can see that we're using some different notation. This is one notation, this is another notation. They mean the same thing in terms of whether or not some ordered pair is in the relation. All right, one more example. Let's say that X is the set of all finite subsets of the natural numbers. And we're going to define a relation E on this collection of finite subsets by saying that for every A and B, which are finite subsets of n, A is related to B provided A intersect B has an even number of elements. And the question is this relation reflexive? We'll prove or disprove. Now, before we try to answer the question, I think what we ought to do is try to understand exactly what is in the relation, meaning what is related to what. Keep in mind that this definition requires that the set X have only finite subsets of the natural numbers. So this set, 1, 2, 3, 17, 29, that's a finite subset of the natural numbers. However, the set of all positive primes is not. There are infinitely many primes, so that's not an element of X. All right, now let's suppose that A is 1, 2, 3, 17, 29, and B is 2, 4, 6. Then if we compute the intersection of these, we get the set that contains just 2. That has an odd number of elements, so that means A is not related to B. One more example. Let's say C has 1, 2, 3, 4, 5, 6, 7, 8, and D has 2, 3, 5, 6, 10. C intersect D will be 2, 3, 5, 6. That has an even number of elements, and so that means C is related to D. All right, back to the original problem. We were supposed to figure out whether E is reflexive. All right, here's the proof. The relation is not reflexive. And as before, we'll illustrate this with a counterexample. A, which has the set containing just 1, is not related to itself because A intersect A is just the set containing 1. That has an odd number of elements. And that's it. We've just shown that this relation is not reflexive by exhibiting a counterexample. Okay, that's all for now.